Hello? Okay. Okay, so Garage. Perfect. Using LLMs to make retrieval smarter. I am a machine learning scientist at Ada, and let's get to it. The idea is that we're going to go through, I don't see the next slide. We're going to go through the retrieval readiness gap. We're going to see what the problem is. We're going to see the idea that we came with. And then we're going to test Garage. We're going to see the results. We're going to see how we formulated the data set and how we formulated the metrics. We're going to look at the results, the production impact, and the benefits that come with this new method. And then we're going to talk about the roadmap of next steps. So most of you are familiar with what RAG is. When we're doing RAG, we're trying to basically split up knowledge pieces into context and embed that context into an index. Then at runtime, what we're doing is we're taking the incoming query, we embed that, and we try to match it and find the best context to answer it. Now, when we do this, we have all-powerful LLMs taking care of making the response, but we are putting a lot of stress in the embedding model. What we have here, as we heard on the keynote, is a static representation of the text. And there's a lot of pressure being put here into finding the optimal chunk that matches that query. And why is that a problem? We have two different cases here. A user comes in and asks, can I open a USD account? And we may see that our embeddings will do a good enough job on the right, and we'll bring up the correct context, and we'll say that, yeah, you can do that. Or they may get confused and bring up context that has to do with a TFSA account, although a TFSA account is never mentioned in this conversation. So what's the problem here? What we're trying to have is helpful and truthful conversations that resolve the customer's issue. And this happens because of the query and context mismatch. There is a fundamental difference between queries and context. Queries are short, they are first person, and they are colloquial. Whatever is in a customer's KB, the passages are long, they are third person, and they are formal. When we embed both parties, what we're trying to do is we're trying for the passage to describe itself, right, inside that static representation. And given the difference in length, whenever we are taking the embedding, we are dividing up with the length of the passage. That means that in our query, every single word matters way more than every word in the context, right? So we are getting back things, an error popped up. We're getting back things that are more diluted. So can we do something about that? Yes, and this is the idea here. We take inspiration from Hide, and I don't know how many of you are familiar with Hide, by raise of hands. Cool. So in Hide, in very brief, what is happening is that an incoming query will come in, we'll put it into an LLM, and then we'll let the LLM hallucinate the matching context. And then we'll match the context to the context. And this is good. This is good in Hide because we are going into the same length and the same representation and the same language. But that has a problem for us in that it is online. So we will be wasting an extra LLM call into making that hallucination. So our idea is to take the whole problem offline. Whenever we are ingesting knowledge, we have enough time and enough compute resources. We don't have any time constraints. And in Ada, we are a platform for customer support. We serve way too many queries, around 50 million queries per month. And this is a lot to start putting more strain on the online process. So That's where the inspiration comes from, and we are taking the whole process of making that good connection between a query and a passage offline. So let's go in and see how this method divides in the process of populating the index, which is the generation path, and then we're going to go into the query, the runtime path. So we have a document, and we use an LLM to start generating multiple questions for that document, from that document, and answers for each of that question. And then we go in and augment that, our index, our database, with the embeddings of the questions. So we do generate question and answer pairs, but we only put the questions in the index. The answers remain just connected to the incoming question. And at runtime, now our index, our database, is augmented with chunks and questions. And as the incoming query will come in, it will go in, and we'll do the semantic search, as we always do. We find the cosine similarity, and we'll rank all our retrieved results, which are now going to be both chunks and questions. And if a question is being selected inside the top n, what we'll do is we go and take back the referenced answer for that question. So we're making a question-to-question match, and during runtime, we're just going to retrieve that answer. And a question here, or a point, an interesting point to be made, is that in this process, when we're generating the questions and the answers, we found a cool, nice way to go about this, in that we are generating the questions, and for the answers, we are not allowing the LLM to hallucinate an answer. Instead, we are asking the LLM to point back to all the reference sources within the document where the answer exists. That means that we are escaping the possibility of a hallucinated answer or of introducing more noise into our database. How do we put this to test? First, we need the dataset, and then we need to define some metrics. For the dataset, we went to our production data, and we took production questions, the retrieved content for all those, and the final answer that we gave back. We went through manual annotations, and from that, we created almost 10,000 annotated samples where we have incoming query, matched retrieved content, and the final answer. And the final answer has been seen by humans, so we know that this is the correct answer, right? And this spans 7 clients, and in total, we are touching around 1,500 articles. And now we also need some metrics. And to do this, the metrics that we define are title match and mass. Whenever we're doing retrieval, there are 2 different things that we need to look out for. One is something like recall. The other one is something like precision. So for the something like recall, we call it title match. And we ask the question, how many times was there content from the correct article that we have in our annotation retrieved in our top n? But this is a metric because it's like recall. As we increase the top n, we can really bump up this number. If we were to retrieve the whole KB, right, that would be 100. We would definitely have the correct article somewhere there. And now there comes mass. And mass stands for mean average semantic similarity. And what it tries to do is that it tries to tame down and penalize bringing in way more context than the context that we actually need. And this is good. Why? Because in LLMs, when we bring in context to make a generation, if we start bringing more and more context, we increase the chances of the LLM using some random piece of information found within the context, somehow connecting it and making it the generation. So we want to be very precise, and this is what mass does. So mass shows us the precision that we have, and title match shows us the recall that this system has. And we go in and baseline our system, and we find that the baseline is at 80% of title match and 14% of mass. And now we start our ablation. We start doing our interventions. First of all, putting in those extra new questions into the index and seeing how these numbers change in our dataset. So we generate and index those smarter chunks. And although title match just improves 2%, what we have is that mass jumps from 14 to 25. 14 means that only a seventh of the content that is being brought in to make a generation is relevant, right? While now, a fourth. So we're doing substantially better at bringing in the correct things. And to continue this intervention and see how our method works with other well-known methods in RAG systems, we introduce re-ranking, which is very common. And we see that Garage, this new augmentation of our index, works quite well with re-ranking as well. And mass moves from 25 to 33%. That means that now a third of the content that is being brought in is relevant to each generation. And this is a big number. And title match goes from 82 to 88. Third, we are doing one extra step, which is we're taking inspiration from a method that was mentioned by Anthropic of contextualizing each chunk. And what they do is that for each chunk that we have in our index, we go in and we make an LLM call. So it's quite expensive, right? This is a very expensive intervention. For each chunk that exists in the index, we make an LLM call and we generate a preceding, let's say, sentence or small passage that brings in the context from the article to that chunk. Imagine a chunk that says our results last year were blah, 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 and then we need to somehow contextualize that they're talking about 2024. This is what that new piece of information does. It says, okay, below are the results of 2024. Oh, our results last year were blah, blah. So now we contextualize. Expensive, but it brings an extra boost. From 33% of mass, we go to 36, and a very marginal title match difference. Now, in different domains, this could be debatable whether it's needed, but in our domain, and since we are, our whole premise is to go towards automated resolutions, we want to resolve customer issues, even that slight bump is really important because it really pays down to it trickles down to the resolutions, to being able to finally resolve the customer issue. And this is the next thing that we do. Oh, no. So first, let's look at metrics again in one place altogether. On the x-axis, we have the baseline, the three interventions. No, here. Baseline, garage plus re-rank, and contextualization. On the column charts now, what you see is two different top-end variations. Outermost columns is top 5. Inner columns, top 3. Title match, the high bars. The low bars is mass. And as you can see, mass at top 5 is lower than mass at top 3. And it makes sense. We bring in more things. We cannot be that precise. And we see that by putting in garage, those numbers jump up. And the most important thing that I would like to take from this graph is all the way on the left, where we see that by doing all three interventions, we are able to surpass the mass at top 3 that garage brings on its own. So our final precision in the context that we bring in for each generation is so much more precise, even though we're bringing 5 now pieces of context than just garage, with our total recall being higher than 90%. Right? This is it's working. It's working well. Okay, so that was the data set, right? And now we are going to the conversations, end-to-end conversations. We're doing customer support. We want to see, do we resolve issues? Do we not? And this is what we do here. This is, we go into our production system, 3 different clients, and we sample for a month. And we rerun all those conversations. And we look at AR rate. AR rate is what we call automated resolution rate. Like, have we resolved the customer issue? Baseline, 36%. Garage at 5, 39%. That 3% jump in the 50 million conversations that we have, that's a substantial number. And the other super nice thing is untruthful rate. And this strictly correlates with the mass metric, right? As we are increasing our number of chunks, we can see that we're able to drop the rate of untruthfulness, the rate at which the LLM brings in information that's not really needed. Because we are bringing more precise information. We're doing an intervention in RAG that's putting it to the right place. And it doesn't cost anything online, right? Everything is offline. And then we ask the question, how do we resolve best? And we can look at the bar charts of the chunk type that's used for resolutions. We have on the left resolved issues and on the right non-resolved issues. So whenever we are resolving, we can see that we are using 60% of the time garage chunks. Nice. What's more nice, I think, is the fact that whenever we are having a non-resolved issue, right, we are trying, but we are not resolving the customer support issue, we get a very good signal. Like when garage is not involved, we can kind of have an aha moment of like, oh, probably we're not going to be resolving that case because garage chunks are not being used. And these are all properties that we found in the system after testing, and it's, yeah, quite interesting. So all these numbers are good. They were all done by us. So now we go with this new thing to a client and we say like, okay, can you test it for us? And they give us some data points. We go offline, populate the DB, rerun them, take them back to them. And from the cases that they gave us, right, non-working cases, they were like, okay, these are cases where our system cannot solve at the moment. We go back, we rerun, put garage in, show them the results, they annotate, and they say 84% of them, of those failed cases, are now being solved. And this costs nothing online. Yeah. So let's go and look into those benefits of generative fast retrieval. What we're doing is we now have an augmented index of questions plus chunks. And this enables two-hop retrieval. It may not be very obvious, but we can now guide particular questions into articles that we want. This is something that RAG doesn't do. RAG is self-referential. A document represents itself, and if you want an incoming query to be mapped to that document, how do you do it? Here you have a very explicit mechanism that you say, okay, this question will now be mapped to this chunk. And whenever someone says something similar to this question, this chunk will come in. Example, someone wants to map, for some reason, questions about weather to an article that talks about a festival. And whenever weather comes in, that festival article will come back. Optimal semantic chunks. We don't have to strive to find the optimal chunk or context to bring in online. This is a tough problem, and it takes time. We can spend that time offline. At ingestion time, where we have all the time in the world, almost, we can go in and slowly and easily crunch down more and more compute and find those optimal semantic chunks. We say, this question has an answer, the optimal answer is this. And of course, we're tapping to the offline pre-processing efficiency, right? This can take, we can scale this, we can parallelize this, it can take 5, it can take 10 minutes. Clients are not going to complain. And this is ideal for high volume, low latency applications, right? And this is what we want. In the customer support domain, we want to be able to instantly respond. And we have way too much volume to think of interventions that add to our online compute. And the next two are very interesting and very, yeah, those are the two things that kind of spiraled this piece of research. And then we came back and we're like, okay, this is now a new product feature that's really, really good as well. So feedback mechanisms. right? Again, RAG. We have an application, we have a chatbot, a question comes in, it tries to retrieve content, that content does not work. We know which article should have been retrieved. Can we somehow make that connection in plain RAG? No. Can we do it here? Yes. And now we have the ability to add the question and the optimal context for it. But at the same time, we have the opportunity to add the exact opposite. Questions that have no answer. So now with this intervention, we enable the system to know exactly what it does not know. So this would be the end of the benefits. And the future investigations here would be enhanced index features, how we can bring in more hierarchical search, and how we can bridge this down with more graphs and so on, and go in and have an extra set of research on custom thresholding for in and out of domain data and so on. The enhanced index features here, one last thing that I would like to say, and then we can open up for questions and discussion, is that right now we have, what we've shown is that in principle, this new hybrid index of questions and chunks works. So why not try out more things? We are in the offline processing part. We are generating questions. Why don't we generate topics as well? Why don't we generate summaries? Why don't we more and more augment that index to the point where we see failure? So yes, questions?
Hi, nice talk. I want to know how do you handle scenarios with like multi-hop queries? I think you mentioned something about like hierarchical or more complex queries, but like at this point, do you handle queries that maybe have context in different documents?
Yes. So we have a question, and the example that I gave about the weather and the festival, right? So we have a question that talks about the weather, and that question maps nowhere in our system because of how the system already has the information that it has already in the index. What we can do is we can take that question and forcefully map it to an article that we want to be retrieved. So then whenever someone asks about the weather, the articles that we want get retrieved. So it's a feedback mechanism for the manager of the system. And it's not an automated mechanism.
And how do you kind of decide the chunk size then?
So we use the exact same, okay. Very good question, by the way. I cannot go all the way back. Here, we use the same pipeline, and from the generated question to the embedding to the database. We take the question, we take the article that wants to be mapped, and we run the exact same paradigm of like, okay, go ask that question and find where the answer is. And in the case of the weather, right, there wouldn't be an answer. In that case, we use the full article. So we force that connection. Yeah. There was a question. Yeah.
Thanks for the great talk. So what have been some effective feedback mechanisms in your experience?
Okay. First and foremost, we, as a platform, we expose these back to the AI manager, we call them. It's the people that manage the bot. So they go in, they look, and they have now the controls to insert new questions, new points where customer questions meet database and so on. And they can also add the negative parts. What we can do is we can also have a lot of, we've done research in more offline processing mechanisms, because this really, it looks a lot like dataset preparation time, right? We are augmenting, we are creating all those training questions, and now we can have automatically taking semantic similarity between questions, between answer chunks, and start pruning, and we can have our own baselines for the optimal performance at creation time. So that's another part. And of course, we can have cases of online queries come in and they get resolved or they don't get resolved, right? And for that, we have an automated system that decides that together with humans. we can have both those systems looping back and start incorporating into the training set as positive cases, positive examples, the training questions that got resolved to those documents, or cases of unresolved questions where it's actually an incompleteness from the KB part. We can include them as negative indexed cases. So 3 different ways.
Thanks for the great talk. I had a question about the smart semantic chunking. I think you kind of already answered, like if your generated question matches up with a chunk in your documents, you save it, otherwise you save the whole document. Is that it, or like what was the smart semantic chunking about?
This stage, right?
Yeah, and like the cycle image you had at the end as well. Yeah, the second
The
part,
optimal.
optimal
Okay.
semantic chunks.
So at creation time, we say that we're trying to generate questions. And those questions can come from 1 article, from 2 articles. We can combine 3 articles in the context of an LLM and say like, okay, where does the answer exist? And the LLM comes back with pointers to the places where the answer exists. And we collate all those pointers and we create the optimal chunk. Because now we don't have to bring in the full article at runtime and let the LLM decide which pieces it should use as context. We are deciding that offline. And the chunk optimality is another measure. I didn't have time to bring it into this talk, that we created together with mass. So how good are we into finding the optimal semantics for each question that we generate? How good is the generation process? And this guided our research in the generation pipeline, semantic optimality. And it was measured as a cosine distance once, and then as an LLM metric, LLM as a judge. So we would put 2 different pieces of context and we say like, okay, which one is better, and the ground truth, and see if one of the 2 was optimal or not.
Well, first, thank you for the presentation. I really like the approach, as I also tried using LLM to enhance retrieval. But one problem I faced was the high LLM cost at very large scale, because you're adding multiple LLM calls for each document. So how did you handle that issue with the client, and were they actually aware of that?
So thank you, very good point. Here we were able to do what? So we generate the questions, and then that could be an LLM call and so on, and then we could have an LLM call for each of the questions to point back to the answers and so on. So that was iteration 1. And then the subsequent iterations, we went down the path of first prompt tuning, trying to squeeze that process into a single LLM call that creates the questions and answers them. And we get back a JSON dictionary. Like, there are ways to go about it in a very structured manner. And then in the final iteration, we were able to fine-tune a model that does exactly that. That knows how to go in, take very good questions, and come back with the perfect way to describe the context, which is, in our case, a list of tuples and stuff like that. So it was first prompt tuning, then few shots, and we ended up fine-tuning the model that takes care of that part. But it's true, it's a pain point. And we were, because of the scale that we have, we are saving, again, 15 million conversations per month. So spending, and you will see that our data set here for 7 different clients was 1,500 documents, 1,500 articles. Okay? So even if we make like 1 LLM call for that, we can pay the best LLMs. It's an acceptable cost. Because at runtime, we are just winning all that back. We could be using O3.
Just a follow-up question on this. You mentioned this contextualizing of chunk was probably inspired by Anthropic or something. Yes. And I recall vaguely that they have some sort of prompt caching, which kind of like makes those repeated LLM calls less expensive. So I was just wondering if you know of any other techniques with other LLM providers that we can leverage to reduce the overall LLM expense.
I think that, very good point. I think that KV caching exists in most LLM providers nowadays. And so they do kind of caching mechanisms, most of them. Like OpenAI, I know it does. Anthropic does as well. So just taking care of the sequence at which we process the data in order to take advantage of that caching. So not just go random tree through articles, but go through, like in a principled manner, in a sequential manner, through all the contexts built for each article, means that the article is now cached. We don't have to recompute. It's faster and it's cheaper, trying to maximize the cache hits. Yeah. Yeah. But, yeah, I don't know of any other ways. Just, yeah, the time domain.